Okay, so I am Harish Krishnani. I am a Prime Minister's Research Fellow at IISER Mohali, and I will be taking your tutorials, you can say, or maybe the doubt sessions for this Algebra second course. And we will be meeting on each Tuesday from 6 to 8. So, yeah, so basically my job will be to solve the assignment problems, but this is the first week, and the first assignment is still due on, I think the last date is 7th February. So we can't discuss that. But what I have planned is maybe we can just go through the lecture notes once. And if you have any doubt regarding that, then you can ask me. And side by side, we will also solve some sample problems. So, yeah. And if you guys have any doubt in any of the topic that is discussed in the lectures, then you can also ask that. Otherwise, I will just go by the chronology that is being followed in the lecture notes. Okay. Okay. So I hope all of you are aware of what is a field, right? So this I think you all know. Now, in this course, uh, the first definition that is being taught is of field extensions. So if anyone is not comfortable with the definition of field, then he or she can tell me. We can just revise it again. Otherwise, we will move to the definition of a field extension. Okay. So no response. I assume that all of you are aware of what is a field. So field extension, as the name suggests, it is an extension of a field. Means there is some kind of another field. Oh, there is some chat. Okay. So as the name suggests, there is something else which contains our original field. So here, by extension, we mean an extension that is a field itself. So uh, a field K is said to be a field extension. Okay, so Sam, you are saying this class session is clashing algebraic geometry solving session from 7 to 9. Okay. Actually, we have to announce the slot uh, in the beginning of the session. So that I have already done. So what you can do, you can just request the NPTEL team. If they come revert back to me with the same request, uh, then I can change, because they have clearly stated that we are not supposed to change the timings, because it's announced on the course web page. So that's why we can't change it of our own until unless there is some emergency. But uh, to change the timing throughout the course, you have to first contact the NPTEL team, and then if they reply back to me with the request, then I can try to change it. Okay, Sam? Okay. So a field K is said to be a field extension of a field F if F is a subfield of K. So simply there is a given field F, and there is another field K which contains F. So means, and it is denoted simply as F contained is K. So this is the given field, and this is the extension of field extension of F. Okay. So notation wise, we can denote it F contained in K, or uh, we will also denote it as a tower. So K is a super field, so we will put it above, and F will lie to the bottom of it. So these are the two notation that we will be following. So observation, immediate observation you can have is uh, K is a F vector space. Okay. So for a vector space, K has to be an abelian group with respect to addition, and that it is already there. And the scalar multiplication is defined in the usual sense. That is, let alpha belongs to F, and say small k is inside K, then alpha dot K is simply alpha K, and that would be inside K, right? Because K is a superfield, so it contains alpha and K both. So just as an element multiplication you can define, and that's how the scalar multiplication is uh, being defined. So uh, it forms a vector space. Now the dimension of this vector space is called the degree of K over F. So that is K F. It is the degree of K over F. It's simply the dimension of K as a F vector space. Okay. I hope that is clear. So let's see quickly some examples. So very common example is to take K to be the field of complex numbers and F to be the field of real numbers. So of course, uh, here you have R is contained in C, right? And what is the dimension of C over R? Anyone? Yes, you are right, Sam. It is 2. So C over R is having dimension 2. Okay. Yes, Vivek, it's 2. Thank you. So what if I replace F by Q? So Q is again a subfield of C. So the it's a C is a field extension of Q. And what is the dimension? Infinity. Yes. So the dimension is infinite. Okay. So yes. So as you all said that you are aware of the fields, so I hope you all are aware of the this notation fx, that is the ring of all polynomials in ring of all polynomials in X right? And in fact, it's a integral domain, right? So this is also you can say the a PID, principal ideal domain, principal integral domain. So uh, maybe I can simply write it is PID. Now, if you have an integral domain, then you can construct a field of fractions, right? The field of fractions of this is uh, so fraction. This is fraction field of fx. So what does it contains? It contains the rational polynomials of the form fx by gx such that gx is not 0. Okay, so it's a fraction field of fx. Now, similarly, one can define what is x1, x2, so on to xn. So it is nothing but the fraction field of f x1, x2, dot, dot, dot. Okay, so now uh, as more examples, you can see that say we are considering a fraction field in three variables x1, x2, x3. So it contains f, it contains x1, and it also contains x2, right? So it will be a field extension of the field, say x1, x2, right? Similarly, it will be a field extension of the field x1, x3, and also a field extension of the field uh, x2, x3, right? And uh, this is a field extension of x1 and also a field extension of x3. Similarly, this is a field extension of x1 and also a field extension of fx2. And this is a field extension of x2 and x3, right? And now all these three are field extensions of f. So you get a diamond of field extensions, right? So I hope now you all understand what is a field extension. So now given a field extension, given k an extension of f, one can think of a substitution map. One can define a substitution map in the following manner. So you have let alpha be inside uh, f, belongs to f. Then define q of uh, maybe I should not write q. Phi of alpha you can define from the polynomial uh, ring to k as a polynomial f of t will be mapped. Sorry, we are in x variable. So f of x will be mapped to f of alpha. Okay. Now, I made a mistake. In fact, we can define it for any alpha belongs to the larger field, that is k. Okay. Now, what you do, you see the kernel of phi alpha, right? So case one is when kernel of phi alpha is not equal to 0. So what does this mean? This implies that there exists a polynomial p of x which is not equal to 0, and inside f of x such that p of alpha is equal to 0. So alpha is a root of certain polynomial in with constants in f. So if that happens, then we say that alpha is algebraic over f. Means it satisfies some polynomial over f. So alpha is said to be uh, alpha is said to be algebraic over f. Now, kernel of phi of alpha is ideal of fx, and as we discussed already, that f of x is a principal ideal domain. So each ideal is generated by a single element. Each ideal is a principal ideal. So kernel of alpha is nothing but the ideal generated by p of x. Maybe we have to just put a mm, so it is generated by px. So here we can also put the condition that it is irreducible and monic. Because even if it is not irreducible, then also it may satisfy P of alpha, but then it won't generate kernel of phi alpha, right? So we have to take it irreducible and monic, and at that condition, it will generate the ideal kernel of phi alpha. Okay. And in this case, we will say that it is uh, alpha is algebraic over f. Okay. Now, case 2 is when kernel of phi alpha is equal to 0. Now, what does this means? This means that for every px inside fx, px is a non-zero polynomial, p of alpha is not equal to 0. So alpha is not a solution of any non-zero polynomial inside fx, and in that case, we say that alpha is transcendental over f. Why the name is so algebraic and transcendental? Algebraic means alpha is not a relation over f. It's not means if you add some powers of f with constant in f, then it is not going to give you 0. That's why the name is algebraic here. One that is not algebraic is called transcendental. Okay. So Now, a quick observation is if alpha belongs to F, then alpha is algebraic over F. Because you can simply take the polynomial to be x minus alpha and then it will satisfy that. So, yeah, here the reason was fx is a PID. Okay, so that is, I think, more or less covers what is being discussed in the first lecture, I guess. Only thing left is to see. So transcendental transcendental numbers are okay. So I will write one more definition because that is also useful. So maybe I can use the yeah. So alpha belongs to C is called algebraic is called an algebraic number if alpha is algebraic over Q, right? And a transcendental number if it is an transcendental number otherwise. So you have C as an extension of Q. So for over that extension, if an element of C is algebraic over Q, then we say that it's an algebraic number. And if it is not an algebraic over, it's not algebraic over Q, we say that it's transcendental. So that's a definition of algebraic number. Now, what if we take the extension over R? So in this case, any alpha belongs to C is algebraic over R. Can any one of you say why? So let alpha belongs to R, then we can take P of X to be just X minus alpha, right? Uh, satisfies P of alpha to be 0. And if uh, alpha is not inside R, but it's inside C, then you can take Px to be X minus alpha and X minus alpha bar. So what it will be as a polynomial, it will be x square uh, minus alpha plus alpha bar x plus mod of alpha square, right? So this is the modulus is always inside R. And what is this alpha plus alpha bar? You can see that this is also inside R. Because if alpha is a plus iota b, then alpha bar is a minus iota b. If you add them, then it will be just 2a, 2 times the real part. So it's going to be inside R. So that's why this polynomial uh, belongs to Rx, right? So that's why the case when C is over R is not interesting, because here every uh, algebraic number, sorry, every complex number is an algebraic number. That's why the definition is uh, defined for the extension C over Q. Now, what is the cardinality of transcendental number? So you can see that algebraic numbers are countable. I should say the set of algebraic numbers the set of algebraic numbers is a countable set. Can anyone just quickly say why? It's already there in the lectures. So I'm not writing it here. I will just say why it is so. So see, something is an algebraic number if it is satisfies a polynomial, right? So now polynomial over Q. So for a fixed natural number n, they, there are just finitely many polynomials of degree uh, less than or equal to n, right? For example, if you consider the polynomial of degree 1, so they are just ax plus b type, right? And a and b are from rationals. So how many polynomials you can have? It's just q cross q. And the direct product of two countable set is again a countable set. Similarly, if you have for a fixed n, how many polynomials of that having that degree exist? It's just you have for q cross q, so on to n many times. If n is the sorry, n plus 1 times, if n is the degree of that, so it's again a countable set. And the degree is a natural number which is a countable set. So what you are doing, you are just if you want to uh, see the cardinality of all polynomials over Q. So it's just the countable union of countable sets, because you have to take the union over n, right? And uh, for a particular degree, you have countable many polynomials. And then if you are taking a countable union of countable sets, then it turns out to be again countable, right? So the set of all polynomials over Q is countable, right? Now, any polynomial have at max n roots inside Q, or you are considering C, so C is algebraic closure of that. So it has all the roots. So any polynomial has n many roots. So it's a finite number. Now what you are doing, you are taking a finite union of countable sets to see all the roots. It might be repetitive, but it may be at max the finite union of a countable set. And that's why it's again a countable set. So the set of algebraic number is a countable set, and that implies that the set of uh, transcendental numbers is uncountable, is an uncountable set. Why is it so? So let's say this set is we denote by a q, right? So what is a transcendental number? It's something which is not algebraic. So this set will be nothing but C minus AQ. Now this has cardinality cardinality equal to cardinality of C. So we will denote the cardinality by this symbol hashtag C minus AQ. So this is countable, and this has the cardinality same as cardinality of R, right? Because it's just R square. So R square is uncountable, R is uncountable, and R square has the same cardinality because we are just taking a finite product. So, and this is countable. So you are subtracting a countable thing from an uncountable thing. That's why this is uncountable. And in fact, it is the same cardinality as the cardinality of R, which is known as a continuum, I guess. So this is also an important observation. You can find this fact as it is in many exams, that what is the cardinality of transcendental numbers. So it's equal to the cardinality of R, and it's uncountable. So that is what was covered in the first lecture. And now lecture 2 we can see. Till now, if anyone has any doubt, then you are welcome to ask. Otherwise, we will move to the next definition. Okay, if no one, let's uh, start with the definition of smallest subfield of K containing F and alpha. Uh, so we will denote F of alpha by it is the smallest field containing F and alpha. Okay, so uh, let's consider the case that alpha be algebraic over F. Okay, it may belongs to an extension K, an extension of F, right? So let's consider the case when it is uh, what to say, it is algebraic over F. Then if you look at the map, uh, the map Q alpha, we denoted by I think phi of alpha, right? The substitution map phi of alpha from Ft to K, uh, then what uh, you will get, you will get so first of all, let's observe what is the image. Image of Q alpha is image of phi alpha. So let's denote it by f of alpha. And why we are doing so? So see what we are doing. We are sending an element p of t to p of alpha. So what in the image will have? Image will have the polynomials evaluated over alpha, right? Alpha an, alpha n, an minus 1, alpha n minus 1, and so on to a1 alpha plus a naught, where this n can vary over natural numbers and also 0, because it may be a constant polynomial, and AIs are all from F, right? So all polynomials evaluated over alpha, if you collect all those evaluations, then this will form the image phi of alpha, right? and uh, also let P of t be the monic irreducible polynomial satisfying alpha. Then what you have by the first theorem of isomorphism, that you have in the domain f of t modulo the kernel. What is the kernel? Kernel is the ideal generated by pt, that we have already seen how the kernel is p of t, that will be isomorphic to the image which is f of alpha, right? Okay. So this you can check that this is a integral domain, right? And if it is an integral domain, this implies that ideal generated by p of t is a prime ideal, right? And as we are in PID, since ft is a PID, so in PID, prime ideals are also maximal ideals. So PT is a maximal ideal as well. And then uh, an integral domain modulo the maximal ideal, what it will give you a field. So this implies ft modulo p by t is a field, and since f of alpha is isomorphic to this implies f of alpha is a field, right? So so that's how we get that this whatever this image is, it turns out to be a field, and uh, this field as a vector space over, yeah. Now one more observation. So we already know uh, f of alpha, this round bracket alpha. What was it? It was just the smallest field containing f and alpha, right? Now and what is this f square bracket alpha? This is the expressions in alpha with polynomial with coefficients in f. So since this is a field containing f and alpha, so field is closed under addition and multiplication. That's you know. Therefore, f of alpha will contain this square bracket, right? Because it is just expressions in elements of f and alpha. So it will definitely be contained in a field that contains f and alpha. Now, this is also the smallest field containing f and alpha. And this f square bracket alpha also contains f and alpha. So it cannot be smaller than f alpha, right? So this implies f of round bracket alpha is also contained in this and uh, square, which implies that these two fields are same. So the smallest field containing f and alpha is nothing but the field which has all polynomials evaluated at alpha. Okay, so that's a nice result. Okay. Uh, Now, similarly, one can see what is parallelly. You can see uh, f of some alpha 1, alpha 2, dot 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 alpha k. You just use the induction is same as, I should not use k because I'm using this notation for the extension. Fn would be nice. Okay. Now, uh, the second case. Let's consider the second case. That is when alpha belongs to the field extension q, sorry, k is transcendental. Is transcendental. Okay. So now again we will consider the map phi of alpha. Consider phi of alpha from ft to the uh, k, right? Now in this case, we know that the kernel of phi alpha is 0, and that implies that f of t is isomorphic to f of alpha. So f of alpha is nothing but the image, right? Image of phi alpha, and which we already know it's just evaluation of alpha over all polynomials. So here we get that f of t is isomorphic to f alpha, and thus f round bracket alpha is isomorphic to the fraction field. Oh, sorry, f round bracket t, the fraction field of polynomials over f is isomorphic to the fraction field with polynomials over alpha, right? Hmm. So as an immediate corollary, we get that if alpha beta belongs to k are transcendental, then the smallest field containing alpha is isomorphic to the smallest field containing beta. I have not written the spelling of transcendental correctly. Okay. So any doubts still here? Okay, I assume that there are no doubts. So one thing I want to mention that although we know that the countable numbers are having cardinality so much that it is has the same cardinality as that of R, but the only um, transcendental numbers that we know are E and pi. So E and pi are transcendental. So that is being proved that E does not satisfy a polynomial over Q and pi does not satisfy a polynomial over Q. But E plus pi is transcendental. That's an open problem. All expect that it should be a transcendental number, but there is no proof available till now for that. So there are many transcendental number, but to prove that something is transcendental is a very difficult job. So yeah, okay. So I think that's it for the second. So, yeah, so there are one or two important theorems. So let me just state uh, those theorems as well. This is from lecture 3. We will solve some problem at the end. Let me just first revise whatever has been covered in the lecture, and then in the end we will see some problems. So uh, let K an extension of F and L an extension of F are two uh, extensions of F, then uh, we say that they are isomorphic, that they are isomorphic if there exists a there exists an isomorphism phi, field isomorphism phi from K to L, that fixes each element of F. So phi from K to L, which is restricted over F, is an identity map over F. Okay. So yes, so maybe we can see some example of this. So I will discuss the same example as discussed in the lectures. So mm, let's K1 be the field Qt modulo T square by minus 2, and it's an extension of Q, right? And K2 be the field Q T modulo T square minus 2T minus 1. So it's also an extension of Q, right? This is also an extension of Q. Now we have to show that they are isomorphic. So one method is to directly define a map from K1 to K2, which fixes Q. The other is you define from K1 to some K3 and K2 to K4, and then show that K3 and K4 are isomorphic. We are going to do the same thing. So from here to here, you can define the map. So phi, define a map from here. Okay, maybe I should use better notation. So define, say phi1 from K1 to the field K3, which is Q root 2. So what it is the smallest field containing Q and root 2, right? So you just define the map Q of uh, root 2. Root 2 bar, maybe you can say, because you are going to send and coset of T square minus 2 to this. So how it will be defined? You send some f of T bar. Bar I am using because it's a coset of T square minus 2. You map it to f bar of root 2. Just evaluate it. So then it will be inside uh, root 2. But I don't think you need bar here. Just evaluate it. It will be inside root 2. And what is the kernel of this map? we can just take simply the entire field. Yes, Qt, just the evolution map you take, and the kernel is then the ideal generated by t square minus 2. So this gives you, here from here also you can bar remove. This gives you that uh, Qt modulo t square minus 2, this is the kernel, is isomorphic to q root 2. And it will fix all uh, rationals, because rationals you can consider as constant polynomials, so it evaluating it over root 2 won't affect the value, it will be just the rational, same rational again, right? And here you can define the map. So what is the root of this? So root is t equal to 1 plus minus root 2, right? This is a mnemonic polynomial of 1 plus root 2. So you define phi 1 plus root 2 from qt to uh, q1 plus root 2, the same manner f of t evaluated on f of 1 plus root 2. So the kernel will be the ideal uh, generated by t square minus 2t minus 1. So this will implies that q t modulo this t square minus 2t minus 1, this is isomorphic to q of 1 plus root 2. And then q of 1 plus root 2 is same as q root 2, because the smallest field containing q and root 2 will also contain 1. So it will also contain 1 plus root 2. So this field is inside this, and the field containing 1 plus root 2 contains 1 plus root 2 and 1 also. So 1 plus root 2 minus 1, it will contain root 2. So this field is contained inside this. This is same as q root 2. Thus, you get that these two fields are isomorphic. So this implies K1 and K2 are isomorphic. Okay, as an implication of both of these. Clear? So now to find isomorphisms is a difficult problem, but once you reduce your like once you or maybe stick the definition of isomorphism, then the problem becomes a bit easier. And here is a theorem which says that if alpha belongs to k and beta belongs to the extension f are such that alpha and beta are algebraic, then there exists an isomorphism k from k to l, the isomorphism phi. Uh, so by an isomorphism, I mean the isomorphism of the field, right? The field extension, such that phi of alpha is equal to beta, and of course it's a field extension isomorphism, so it will fix all elements of f. So such an isomorphism exists if and only if the irreducible polynomial of alpha over f equals the irreducible polynomial of beta over f. Okay, so this is a characterization of all isomorphisms sending alpha to beta, right? So this is a very important theorem. You can keep this with you. Another interesting statement is uh, this, that phi be from K to K bar a field or is an isomorphisms of the field extensions if alpha belongs to K uh, and some f of t belongs to uh, is a polynomial in the coefficients from capital F are such that alpha satisfies F, then phi of alpha will also satisfy F, right? So these two statements will be very useful when you will computing the degree of extensions. So as I said, the name, let me just define. So we have already seen, right, that the degree of extension is just a dimension of the larger field as a vector space over the smaller field. So that's what was discussed in lecture 4. So I'm not repeating it again. I will just define what is a quadratic extension. Quadratic extensions. So as the name suggests, quadratic means of 2. So any extension of degree 2 is, so it's an extension of degree equal to 2. Okay. So then, okay. So one important observation is this, and this is being used in, I think, some of the problems. Suppose KF is a K2F is a quadratic extension, then you can see that uh, there exists some D inside F such that uh, just a minute, K is equal to such that K is equal to F root of D. Okay. So definitely this root T, root D will not be inside F, because if it is inside F, then it will be just F, right? So D is inside F, but root of D is not inside F, and K is nothing but the smallest field containing F and root D. So any quadratic extension is just an extension of this type. Okay. Now, uh, let us see what is a tower of extension, although we have already seen it in some sense, but uh, just recall it because then we can see one important theorem. The tower of extension means you have some field F, then you have some extension K1, and then you have some extension K2, and so on to you have some extension Kn. So this is a tower of field extensions. Tower of uh, field extensions of F. Okay, so now an important result that is being proved in the class says that if F is a subfield of K, which is a subfield of F, then you have the degree of, sorry, here we should have some other field, maybe L we can take. The degree of L as a vector space over F is the product of degree of L over K and the so L contains K, K contains F. The degree of L over F is the product of the degree of L over K and K over F. So this you should keep it with you because it will be useful. And one immediate uh, corollary of this, so you can write it as a theorem perhaps. Then uh, you get a corollary of it. Immediate corollary is, so say alpha belongs to K of F, then you have one more thing. And the dimension of K over F is less than infinity, then you can see that K contains F of alpha, which contains F. Okay. So if the dimension is less than infinity, it implies that every element is algebraic over F. That is an exercise for you. Maybe it's an easy thing to check if any finite extension has is an algebraic extension, which means it every element is an algebraic element over that smaller field. So every element is algebraic over F, and that's why the F of alpha is of has a dimension. uh, F of alpha over F has finite dimension, and it is contained inside K. So by the above uh, theorem, what we get, K over F is K over F alpha, and F alpha over. So what does this tells you? This tells you that the dimension of F alpha over F divides the dimension over of K over F. Okay. So what if the dimension of K over F is a prime number? So if it is a prime number and alpha is inside K but not inside F, so F of alpha over F cannot be the same field again. So it has to be something larger than F, and it should also divide the dimension of K of over F, but K over F is a prime number. So the only possibility is F of alpha has to be same. Okay. So I think now we can solve some questions because uh, uh, otherwise we won't be able to solve something because the next lecture was on constructible numbers, and maybe that we can see some times later, right? So because if we discuss, we'll start discussing that, then we won't be able to see any uh, examples or any sample problems. Okay. So maybe let's start discussing some problems. Let me just write a. So what you guys can are seeing right now, is it the note or the question? Hello, can anyone quickly respond? Let's reshare. Okay, let me write one question for you, and you try to answer it, maybe verbally or by typing in the chat, and then we will also solve it. So yeah, the question one is, if alpha is the cube root of 2, then find the irreducible polynomial of 1 plus alpha square over q. You may not, so you know what is a irreducible polynomial of one of cube root of 2, but you need to find what is the irreducible polynomial of 1 plus alpha square. So irreducible polynomial of some number means the irreducible polynomial, monic irreducible polynomial that satisfies that element. Yes, anyone? I think degree will be of 6. No. So hint is, it's again a polynomial of degree 3. Yes, Vivek. What is polynomial? Can I say yes? You can of course say
Sir, it's x cube
yes,
minus 3x square
yes.
plus 3x minus 5.
Okay, good. How you get it?
Sir, first I have find alpha square
Alpha square, good.
and then add with plus one both side. And it will be alpha square plus one.
Okay, and then
And now, so this is our x. Alpha square plus one, this is our x.
this is our x,
Yes.
and then you are trying to find some relation in powers of x.
Yes. Yes, sir.
Okay, so that's what we are supposed to do. So solution, so as Vivek said, so let x be 1 plus alpha square. So what we will do now, we will be considering a basis. Okay, so try to form a basis of using this x, means how much powers of x are linearly independent. So what is x square? X square will be 1 plus alpha whole square, that is 1 plus 2 alpha square plus alpha 4. But uh, alpha cube is 2 alpha square plus alpha cube dot alpha, and alpha cube is nothing but 2, right? Because alpha is cube root of 2. So it is 2 of alpha, right? Then this is something which is not expressible as x or 1. So you have basis 1, x, x square also you have commuted. Now x is clearly not expressible as 1. X square is also not expressible as the linear sum of 1 and x, because it contains some powers of alpha square and uh, not alpha, and it has some power and it has a term in alpha, right? So we have to compute x cube also. So what is x cube? X cube is 1 plus 2 alpha square plus 2 alpha times 1 plus alpha square, right? So what you will get, this will be 1 plus alpha square plus 2 alpha square plus 2 alpha 4 alpha square plus 2 alpha 4 plus 2 alpha plus 2 alpha cube. This will give you 1 plus alpha square, 2 alpha square, 2 alpha 4 is 2 alpha 4 is 2 times
4 alpha.
4 alpha, right? This is 4 alpha plus 2 alpha, and 2 alpha cube is 4.
4.
Yes. So this is 1 plus 4, sorry. So this is 5 plus 6 alpha plus 3 alpha square, right? So now we can try to find a relation between 1x, x cube, x square. So what base, so now we have x cube also. So try to write these things as a vectors in 1 alpha and alpha square, because they are linearly independent over q, that we know, and alpha cube is nothing but 1. So we just need to consider this thing 1 alpha and alpha square. So from here also only you can get that it's a polynomial. The irreducible polynomial will be of degree less than equal to 3. Why? Because these terms are in 1 alpha or alpha square, right? So three elements having uh, like variables 1 alpha and alpha square, they are, what is the maximum dimension that it can have? It can have maximum dimension to be 3, right? After 4, it as soon as you will reach x cube, it has to be linearly dependent. So from here only, you can guess that that the degree of the polynomial has to be less than equal to 3, because they are terms in 1 alpha alpha square, right? So so 1 is nothing but you can write 1 0 0. Yes, sir. Okay. And what is x? X is 1 plus alpha square. So this is 1 0 1, right? This corresponds to this. Now x square corresponds to 1 2 alpha square 2 alpha. So that is 1 2 and 2. And what is x cube? X cube corresponds to 5 6 3, right? Now so these three are linearly independent because they have 0 at different places. It does not have a 0, it has a 0 at different place, and it has two zeros, so they have to be linearly independent. And this has to be linearly dependent because they cannot have a dimension of 4. So see, this has 6 here, and they have 0 at the second place. So we have to multiply this thing by 3, right? So equate the second coordinate. And now this is 6, this is 6. So once we do that, so now let's see the last coordinate, because here it is 0, here it is 1, and 3 into 2, it becomes 6. Here it is just 3. So to equate it to this, we have to also multiply this to 3. Agree? So,
Okay, sir.
so here it is 3. Or maybe I am doing something wrong. It becomes 6. uh, Minus 3, I guess, right? I have to subtract it. So I have to multiply it by minus 3. Now it is minus 3, 6, it is 3 again. Okay. Now only coordinate that remains is the first one. So here I have 1 minus 3, that is uh, minus of 2, and then plus of 3. So that is 1, and I have to make it to 5. So I will multiply this by 5. So that gives us 5 is the constant thing, minus 3x plus 3x square equal to 3x cube. So is it correct? That the polynomial is 3x, oh sorry, it should be x cube, right? Because we didn't multiply anything to x cube. So it is, uh, this gives us x cube minus 3x square plus 3x minus 5 satisfies 1 plus alpha square over cube. And why anything less than that, any polynomial of smaller degree won't satisfy 1 plus alpha square? Because that's how we have constructed it. Before x cube, 1x and x square, they are linearly independent here. So there is no possibility of a polynomial in of degree less than equal to 2 to satisfy 1 plus alpha square. So that's why it has to be, uh,
Sir,
yes,
I think x cube is linearly dependent, na?
yes, x cube is linearly dependent.
Okay, okay, then fine, fine, sir.
So that's why I have written
Yeah.
x cube is this.
Thank you, thank you. Sir.
Maybe just to avoid notational confusion, I think we should not use x because it's a variable. Let us just use something else, maybe t or something, and then the polynomial we will write as this is t square, and this is t cube. So 1 t t square t cube, and then here it will be 3t 3t square, and this t cube. So x cube minus 3x square plus 3x minus 5 satisfies 1 plus alpha square over q, and uh, by our construction we we are sure that uh, this is also the minimal polynomial or irreducible polynomial satisfying 1 plus alpha square over q. Okay, I hope it is clear.
Yeah, fine, sir.
Okay, now the second question, maybe you guys can try. So similarly, find the irreducible polynomial of root 3 plus root 5 over q. So first thing to observe is that uh, root 3 is not inside q of root 5, which is of the form a plus b root 5, such that a and b inside q. That you can see. Why? Because if that happens, that you can clearly say that root 3 plus root 5, as root 5 is inside this, root 3 is also inside this. So root 3 plus root 5 is inside q root 5. So it will have degree 2 over q. So the polynomial will be having a degree 2 over q. But that's not the case. First of all, we have to see that root 3 is not inside q root 5. So for that, uh, see that if root 3 is of the form a plus root 5, then you can take uh, the square both side, and squaring both sides, you will get 3 a plus 5 b square, uh, 5b square plus 2ab root 5, right? And this implies root 5 is equal to 3 minus a minus 5b square upon 2ab, right? And see, of course, a and b cannot be equal to 0, right? Because if a is equal to 0, then root 3 is a scalar multiple of root 5, which is not the case. And if b is equal to 0, then root 3 is a rational number, which is also not the case. So a and b are not zero numbers. So you can divide it by 2ab. And this gives us that root 5 is a rational number, because a and b are rational number. Is a rational number, and which is a contradiction, right? Parallelly, you can see that root 5 is not inside q root 5. Oh, sorry, root root 3. Now try to see what is the degree and what is the irreducible polynomial. Yes, anyone?
Sir,
Yeah.
I think degree will be 4.
Degree will be 4. And what is the polynomial that you are getting?
The quadratic is alpha 4 minus
Alpha 4 minus
16 alpha square minus 4 plus 4.
how you are getting that?
So by using the simple exponential rule,
And what does this mean? Simple exponential rule?
that first of all is squaring both the sides.
Hmm.
And then in the RHS, we get 3 plus 5 plus 2 root 15.
So means you are just doing the same computation as.
Yes, with the first problem.
Okay. So let me solve it for others.
Sir, one question.
Yes, Vivek.
So that is, we have to uh, transfer the given alpha. That
Trans
is, we have to find the basis of the
hmm,
polynomial, na?
of the polynomial. Yes.
And that is the problem, sir. So please, you have to clear.
Uh, that is actually not a problem. Let's see it. Then you will see. So
Okay.
what we will do? So one thing we have understood that root 5 and root 3 are linearly independent over Q, right?
Yes.
So root 5 and root 3 and also 1 and if their multiplication also root 15 are linearly independent over Q, right? Any doubt, Vivek, in that?
So this is the question that,
See, root 5 is not a Q multiple of root 3, right?
yeah,
And similarly, so these three are linearly independent.
1 root 3 and root 5. Yes, sir. It is
And,
right.
and root 15 is what? This is just root 5 times root 3, na?
Yeah. Multiplication of 2, that
Multiplication of
numbers.
2. And it is also like root 5 is not some rational times root 15. It's some irrational time root 15. And same is root 3.
Yeah.
So these four are linearly independent, right?
Okay. So, sir, can we take it in division form in under root 5 or divided root 3?
This way you want to write?
Yeah.
This is okay. It is just equal. So that's what I'm saying. Root 5 and this is they are rational multiple of irrational multiple of each other. So they are linearly independent. Same root 3 and this is a irrational multiple of root 3. So it's linearly
Sir,
independent.
can we take here the divided form, that is root 5 divided root 3, or root 3 or root 5?
That will be same as taking this. No problem. Because see, if you take root 3 by root 5, then what is this? This is you are multiplying this number by 1 upon 5, right?
Okay. And
So
that is a rational number, 1 by
that is a
5.
rational number. So these, this are uh, linearly dependent over Q.
Okay, now, yes, sir. That is fine.
Okay. And
Yeah.
using root 3 and root 5, you cannot like generate more uh, linearly independent things, because if you add them, then definitely it's a linear combination, right? Or you
Hmm.
multiply it with uh, some scalar that is also a linearly independent. Only thing is root 15 you will get. And now what you do, you take t to be root 3 plus root 5, right? And
Yes.
let me just change the order, put it here, root 3 and root 5. It won't affect anything, but just for the convention. So as a notation, means as a basis, what it is this? This is 0, 1, 1 and 0, right? Root 3 and root 5, right?
Okay, sir.
And 1 is nothing but 1, 0, 0, 0. Now what is t square? T square is 3 plus 5 plus 2 root of 15. That is 8 plus root of 15. So it will be 8, 0, 0,
0, 0, root 50.
not root 15, it's 2.
2.
Root 15 is the basis element, right?
Yeah, yeah.
So these are linearly independent because zeros are at different positions, right? What if I take t cube? Uh, so now whatever power I will take, it can have terms in 1, root 3, root 5 and root 15 only, right?
Hmm.
So one thing is guaranteed that the degree of so it has maximum 1 t square of the powers, they can maximum have linearly independence up to t cube, because 1, 2, 3, 4 they form a basis, right?
Yes, sir.
So so the degree of the polynomial has to be less than equal to 4. So
Sure.
let's see what t cube gives. If t cube is not a multiple of is not a linear combination of 1 t square, then t4 has to be. Okay.
Yes, sir.
So the t cube is root 3 plus root 5 times 8 plus 2 root 15, and that gives uh, 8 root 3 plus 8 root 5, and then this is 2 times root 3 root 15. So it will become 6 times root of 5, and then 10 times root of 5. It will be root so 10 times root
8
of
root
3.
3, 8 root 5,
Root
2, 3,
3.
6 root 5, 3,
So it will
plus
be
5, 2 z 10 root 3. Yes.
18 root 3 plus 14 root 5. So it will be
Okay. Now it will give 1, 18,
0, 18,
14, and
14,
0.
0. So is it linearly dependent or independent?
It will be, yes, sir. Li.
Because only these two have non-zero, only this vector has non-zero positions here and this vector. So they are not scalar multiple of each other, right? One is
Hmm.
18 times and other is 14 times. So it's again linearly independent. So T4 we
Yes,
have
sir.
to compute, which is just squaring this. What it gives? 64 plus 2 root 15 square is 15 times 4. That is 60.
60
And then their
plus
multiplication 32 root 15, 2ab, right? So what it is now, this is 124 plus 32 root 15. So it will give 124, 0, 0,
0, 0, 32.
32. Yes. So it has to be linearly dependent because now we have reached to the maximum uh, stage.
8 alpha square, t square. 32. Okay.
So for 32, t square. So here you don't have uh, non-zero number here. Here you have 2, and here there is nothing non-zero. Here it is nothing non-zero. So this thing has to be multiplied with 16, right?
Yes, sir.
You will always get a monic polynomial. That is also
121.
an interesting thing. So we need not to worry about this thing. You need not to multiply this last one with any number, because you are guaranteed to get a monic polynomial. Okay, so you just
Okay, sir.
multiply these coefficients. So the last one is balanced. Now we have 14 here. The problem is we multiply. Are we missing something? Because
Square is 8 plus 2 right. Cube 64, 60. Alpha 4 is correct.
so 16 into 8 is
128.
8, and here we have 124.
4.
So if we add this 4, then
Yes, sir.
it will be balanced. We don't need this t cube one, right? So
Yeah.
this implies
16
t4 is equal to 16
t
t
square
square plus 4,
plus 4. Yeah.
right? This
Yeah.
implies x4 minus 16x square minus 4 is the irreducible
Polynomial.
polynomial of root 3 plus root 5 over q. You need not to worry about the irreducible one, because the lower ones are not giving you a relation, right? If it is
Yes,
a
sir.
irreducible one and root 3 plus 5 is a factor of the smaller one, then we should have get a relation here, right? So
Yes.
that's why it guarantees the irreducibility, and also root 3 plus root 5 is a solution. Okay, so this method is, that's why uh, more efficient.
Yes, sir. Thank you.
Let us see maybe one more example we can see, and then we can stop. We still have 15 minutes left. Okay. Yeah, that is now that this you should try, because that will develop your understanding in a better way. So find the minimal polynomial. Find the minimal polynomial of the same number, root 3 plus root 5 over q root 15. Okay, so just see if you can get minimal polynomial of root 3 plus root 5 over q
15.
root 15. Same trick you can use.
Okay, sir.
The only point to note here is the root 15 is now uh, not a linearly
Element of,
the
yeah.
field. So 1 and root 15 are linearly dependent. You get?
And
Because root 15, you can multiply the coefficients by root 15. That's even easier than the previous ones. Try the same thing. Here, 1, root 3, they are linearly independent. But what about root 5?
It is also linearly independent.
No, root 5 I can write as root 15 times root 3 minus, yes, let me just see what it will give. Not minus, root 15 by 3, right?
Okay. Yes.
Root 15 and root 3 will be root 45, which is 3 times root 5, and then you can divide. Because now you have this scalar inside this, na? This is inside your field.
Yes. Q root 15.
That is what have created the
The
difference.
member of Q root 15. Okay, sir.
So this is not linear independent, and similarly root 15 is not linearly independent. Okay? So
Yeah.
it can, this cancel, this cancel. Only you have two elements in the basis. So the maximum degree can be uh,
True.
2. So since you can see that root 3 plus root 5 is uh, not inside q root 15, that you should check. Therefore, uh, the minimal polynomial has degree greater than
True.
equal to 2, because it's not inside the field, so it cannot be of degree 1. And this gives that minimal polynomial has degree less than equal to 2, but because the basis is of dimension at 2, right? So these two facts together tells you that minimal polynomial is of degree 2. So even without computing the minimal polynomial explicitly, uh, you can directly say ki what is the degree, right? Right. So the same technique can also compute the minimal polynomial. Let t is equal to 1 plus, sorry, root 3 plus root 5. So it's not inside. Uh, so as a basis, what it will be? This will be uh, so 1 is 1 times 0, right? Root 3 is
Root 3 is Li. Okay.
root 5 is root 15 by 3 times root 3,
Root
right?
3. Yes, sir.
So this is 1 plus root of 15 by 3
Upon 3.
uh, root 3. Okay. So
Yes.
so as a basis, as a vector, this is nothing but 0, 1 plus root 15 by 3, right?
Hmm.
Now, so they are linearly independent. Of course, 1, 0 and 0 something. What is t square? T square is 3 plus 5 plus 2 times root
Root
15.
15.
Wait, 8 plus 2 of root 15, right? So this is nothing but 8 plus 2 root 15, 0. So multiply this thing by this, and then you will get this. So you need to multiply this by 8 plus 2 root 15. You will get, this implies t square is equal to 8 2 root 15, which implies x square minus 8, it should be plus 8 minus 2 root 15 is irreducible polynomial of root 3 plus root 5 over q root 15.
Root 15.
ठीक है?
Yes, sir.
Okay. So how much time we left? Still 5 to 6 minutes are there. Maybe we can just, I can give you some idea of another question which is going to be important in the upcoming lectures. So it's good to note down that question also. So let zeta of n is the nth root of unity, the primitive root. So this is we call as the primitive root of unity. This is a complex number, right? So then can you compute, determine uh, q adjoined with this zeta n over q, the dimension degree of this for n equal to say 1, 2, 3, 4, 5, and maybe 6 also. So what is n for n equal to 1?
Uh, 1.
So the zeta 1 is nothing but 1 on 1 itself,
Yes, sir.
right?
Yes.
Hmm.
2.
One root of primitive root, nth root I should write here. One root of unity. So one root of unity is just the solution of x minus 1. That is nothing but 1, right? So
Yes,
that
sir.
gives this to be 1. Then what is zeta square? Zeta 2, sorry,
Theta 2 will be pi by minus 1.
minus 1, right? And means it's just a solution of x square minus 1, the primitive one. It is
X square minus 1.
x square minus 1. So it's a solution of xn minus 1, right? And that solution which generates all others. That's why the primitive
Okay.
word is there.
Minus 1. General solution, no, sir, we can say.
No, the primitive means it's kind of you cannot break it further. It's not a power of like it will generate everything. Like in x cube minus 1, you also have you have 1 as a solution, but the zeta 3 is some generates the other two also. Zeta 3 square, and zeta 3 cube is 1. So that's why
Okay.
zeta is 3 is the primitive. Say if you consider n equal to 4, then iota is the primitive root, primitive fourth root, because iota is 1, iota square that is minus 1 is also a root, iota cube that is minus of iota is again a root, and iota 4 that is 1 is also a root. So it generates all others. So zeta 2 is -1 because there are two roots possible, only 1 and -1. -1 is the primitive one. So again, the degree is 1. What if zeta 3? So that is the cube root of 3, cube root of 1. So here,
Mm.
can you say something about the degree? So this satisfies x cube minus 1, which is equal to x minus 1, 1 plus x square, right?
Yes, sir.
Now, zeta 3 is not equal to -1. So it won't satisfy this. So it will satisfy this one only, right? So
Yes, sir.
zeta 3 will satisfy
1 plus x
x
square.
square. And uh, you cannot further factorize it because zeta 3 is not inside Q, right? So
Okay.
since zeta 3 is not inside Q, therefore the minimal polynomial of zeta 3 must have degree
2.
greater than equal to 2, right? And you already have it to be a polynomial satisfying this zeta 3. This implies 1 plus x square is the minimal polynomial of zeta 3. And then what is the dimension of Q? Zeta 3 over Q. This is 2.
2.
What if it is 4? Zeta 4 is iota. So it
Iota
satisfies
4.
what you are saying.
It will be x4, zeta 4.
Zeta 4, then
Uh, I think it's degree. No, no, no.
is degree.
Will be 4.
No. So it satisfies x4 minus 1, right?
Is
Which
equal
is,
to 0. Yeah.
that is equal to this, and which is same as uh, x square minus 1 and
X square plus 1.
plus 1. So this gives you two things, 1 and minus 1, and iota is not equal to this. So iota satisfies this.
X
And
square plus 1.
that you can easily see iota square is -1 and -1 plus 1 is 0. Satisfies x square plus 1. Again, uh, same thing will hold, that it is not inside Q, so its degree has to be greater than or equal to 2, and thus 1 plus x square is the minimal polynomial of
Zeta 4 x.
uh, zeta 4, that is eta, and thus Q zeta 4 over Q is 2.
2.
What if zeta 5, that is fifth root of 1, a primitive one? So it satisfies uh, zeta 5 minus 1. So that implies that and zeta 5 minus, sorry, I'm doing, it satisfies x
X5 minus
minus
1.
1 and x5 minus 1 is equal to x minus
X
1,
minus 1.
1
X
plus x
plus
square
x square
is
plus
x4.
plus x4.
Okay, so This cannot be the case because the
Yeah.
primitive, and you will see in the upcoming lectures, we will see that this is irreducible over Q in the upcoming lectures.
Okay, sir.
I think you might have already seen Eisenstein criteria. If not, then this is irreducible due to the Eisenstein criteria, something which we will see in the upcoming lecture. So, uh, so it satisfies an irreducible polynomial means it's an irreducible. So 1 plus x square. Oh, something I missed. Here x cube should also come. X cube plus x4. Okay. So plus x cube plus x4 is irreducible over q.
Yeah.
Is irreducible polynomial of zeta 5 over q. So इस केस में क्या होगा in this case zeta 4 q has dimension 4.
Okay. So zeta 5.
Zeta 5, zeta 5. Thank you. So this is zeta 5. So now the last one is zeta 6, and zeta 7 you can see similar to zeta 5. There also it will be uh, uh, s- here we have 5 minus 1, that is 4. There we have 7 minus 1, that is 6. But the zeta 6 is bit different. It satisfies
Sixth root of unity.
it's a 6 probability, so it satisfies x6 minus 1, and x6 minus 1 is equal to x cube minus 1 and 1 plus x cube. This is like a square minus b square, right? So a minus b and a plus b.
Yes, sir.
So here you have
So that plus a plus b
1
and root plus
minus
1
and
minus
zeta
I plus I
zeta 3 and zeta 3 square.
square x cube 3 to 5.
What you are saying?
I think, sir, it degree will be 5, I think.
No. See, what are the roots of this polynomial? This takes you to the case
1.
of zeta 3, right?
Mm.
So the roots are 1, zeta 3 and zeta 3 square.
Okay.
So these are not equal to zeta 6 because zeta 6 is a primitive root. It will generate all other roots, but they are
X
not
cube
generating.
minus 1.
They are zeta 3 will generate zeta square and 1. And same zeta 3 square will generate zeta 3 and 1 will not generate any other. So they cannot be the primitive roots, right? Uh, so this polynomial will be satisfied by zeta 6. Zeta 6 will satisfy
Okay, 1 plus x cube only.
this polynomial. Yes. And one again we will see that this is irreducible. So this will implies 1 plus x cube is uh, is the irreducible polynomial of uh, this over q. And if you want to see what is zeta 7, then you can check that 1 plus x square plus x cubed plus x4 plus x5 plus x is same. This polynomial is irreducible due to Eisenstein criteria, and that we will see in the coming lecture, is the irreducible polynomial of this number over Q. Okay, I think it's a good time to stop. Maybe if you have
Thank you, sir.
any doubt, then you can ask.
No, sir, I think today's session is very good.
Thank you. So we will be meeting on each week, Tuesday, 6 to 8. So you are welcome to join. And in the next lecture also, because that will be on, I think today is 30, so it will be on 6th. So that will
Yes,
also be before the assignment due date. That is, assignment due date is 7th Feb. So in that lecture also, we will first revise the week 2 lectures, and then we'll see some sample problems for week 2 assignment. And then after that, we will be solving the assignments whose due date has been passed from third week onward. Okay.
yes, yes, sir.
Okay, if you have any doubt, then also you can ask in between the discussion. Okay.
Yeah.
Okay. Bye.
Thank you, sir.
Bye.
Thank you.